All right, today we're going to dig into a really fundamental challenge in digital communication. How do you keep time? I mean, how does a receiver actually know when one bit ends and the next one begins? We're going to explore a classic solution to this problem called RZ coding.
So let's just jump right in with a question. Imagine a digital signal is having a really, really boring day. It's just sending a long, endless string of ones, or maybe a long string of zeros. What's the big deal? You'd think that would be easy to handle, right? Well, it turns out that kind of monotony hides a pretty serious danger.
You see, with a basic kind of code, something like non-return to zero or NRZ, a long string of ones just looks like a constant high voltage. A string of zeros, a constant low voltage. The signal just flatlines. There are no changes, no edges, no ticks of a clock to follow. And that digital silence, that's a huge problem.
And this gets us right to the heart of the matter, what we call the clock synchronization problem. Honestly, it's one of the most critical hurdles you have to overcome to get two digital devices to talk to each other without messing everything up. Think about it like two musicians trying to play a song together but without a conductor or a drummer. If one of them has a slightly faster internal rhythm, they're going to fall out of sync pretty quick. It's the exact same thing here. The receiver's clock, without any timing clues from the signal itself, just starts to drift. It might start sampling the signal a little too early or a little too late, and suddenly it's reading ones as zeros and zeros as ones. The result? Total data corruption. It's a mess. So how in the world do you solve this? How do you force a signal to carry its own timing information, especially during those long, boring stretches? Well, the answer is this really elegant little trick called the return to zero rule. It was designed for systems where getting the timing right is absolutely everything. And you know what? The name pretty much gives the whole game away. With return to zero or RZ coding, you make a simple promise. No matter what bit you're sending, halfway through that bit's time slot, the signal will return to a neutral 0-volt state. It's a simple rule, but it has some really profound effects. So here's the two-step dance. For the first half of a bit's lifetime, the signal does its job. It goes high for a 1, for example. But then, for that second half, it has to drop back to 0. It's a mandatory reset, every single time. And this is my favorite way to think about it. RZ coding basically gives the data stream its own built-in metronome. That return to 0 that happens in the middle of every single bit, that's the tick, or the talk. It's a predictable, constant heartbeat that the receiver can just lock onto, which guarantees it never, ever drifts out of time. Pretty clever, right?
Now, this whole return to zero idea isn't just a one-size-fits-all thing. It can be implemented in a couple of different ways. So let's take a look at the two main flavors you'll see, unipolar and bipolar RZ. Okay, first up is unipolar RZ. It's the simpler of the two. A 1 is a positive pulse that, you guessed it, returns to 0. But a 0, well, a 0 just stays at 0 for the whole bit period. Now, wait a minute. Do you see the problem there? If you get a long string of zeros, what happens? The line goes flat again. We lose that crucial heartbeat. So unipolar RZ, it doesn't quite solve our whole problem. And that brings us to bipolar RZ, which is way more robust. Now we're playing with 3 voltage levels. A 1 is a positive pulse that returns to 0, but a 0 is now a negative voltage pulse that also returns to 0. What's so cool about this is that now every single bit, whether it's a 1 or a 0, creates a distinct pulse. There's always a transition, always that heartbeat. This absolutely guarantees clock recovery. So let's just put them side by side. Unipolar is definitely simpler, but it has that fatal flaw with long strings of zeros. Bipolar RZ, on the other hand, it's a bit more complex. You need circuitry for 3 voltage levels, but it gives us what we really, really want. Guaranteed, rock-solid clock recovery, baked right into the data stream itself. Okay, so this sounds perfect. A self-clocking signal, problem solved, right? Well, in engineering, there is no such thing as a free lunch. This amazing reliability, it comes at a pretty significant cost, and that brings us to the bandwidth penalty. The original source text actually explains this perfectly. It says that because you're changing the voltage level back to 0 in the middle of every single bit, you're effectively doubling the frequency of the signal. And what does that mean? It means you need more bandwidth. And that's the major downside to this whole approach. And that's the bottom line. Let's put a big number on it. 2 times. Because of that mandatory transition in the middle of every bit, you're forcing at least 2 signal changes per bit, where a simpler code might only need 1. This doubles the highest frequency in your signal, meaning RZ coding eats up twice the bandwidth. Ouch! So, let's pull all this together. What is the fundamental trade-off that we're making when we decide to use RZ coding? Here's the final verdict, nice and simple. On the plus side, it's a brilliant solution for the clock synchronization problem. It embeds that timing signal right into the data. But the price you pay for that rock-solid timing is a big one. It costs you double the bandwidth. It's the kind of choice you make when timing is absolutely everything and you've got bandwidth to spare. And this brings up a classic engineering dilemma. RZ coding proved that you can solve the clock problem, but that bandwidth penalty, that's just too high for a lot of applications. So that leads to the next logical question. Is there a way to have your cake and eat it too? Can you get that reliable clock sync without having to sacrifice all that bandwidth? Well, the answer, of course, is yes. The hunt for that perfect balance between timing and efficiency led engineers to the next major step in the evolution of line codes, something called Manchester coding. But that's a story for our next explainer.